All right, today we are going to be talking about atomic mass, and we're also going to be talking about ions. So what atomic mass is atomic mass is the weighted average of the masses of the isotopes in a naturally occurring sample of the element. So what that means is if you have two isotopes, you've got carbon 12, right, and you've got carbon 14. So if I write those nuclear symbols, remember, you've got your atomic number, six protons. You've got your mass number up here, which is protons and neutrons, okay? So you have the same number of protons, right, 6 and 6, but you have different numbers of neutrons. That's what an isotope is, okay? So over here, your isotope is going to be the same number of protons, different number of neutrons, okay? And what atomic mass is, it's the weighted average of the amounts of those isotopes that are naturally occurring. So of all the carbon in the world, a certain amount is carbon 12 and a certain amount is carbon 14. So when you take the average of that, it ends up being your atomic mass. That's what the decimal number is on the periodic table. So it's going to be a decimal because it's a weighted average, okay? So another way of thinking about it, it's the average mass of all the isotopes of an element, okay? That's kind of the easier language to remember. It's the average mass of all the isotopes of an element. All right? Okay, so we're going to do two examples now. The first example has to do with rubidium, and this one is a little bit easier than the next one. Okay, so rubidium has two common isotopes, rubidium-85 and rubidium-87. Okay, if the abundance of rubidium-85 is 72.2% of the whole world, and the abundance of rubidium-87 is 27.8%, what's the average atomic mass? Okay, so what I'm going to do is I'm going to take my mass numbers, okay, I'm going to take my mass number and I'm going to multiply it by my percent abundance, and that's how I'm going to calculate my atomic mass. All right, I'm going to do that for each isotope, and then I'm going to add them up. So sometimes we call that a sum, right, and we use this little sum figure. I don't know if you guys have learned that in math yet. It looks a little bit like a dragon or a dinosaur or something, right? And he's chomping at them. But really what it means is you do this for each isotope and then you add them up, okay? So what I'm going to do is I'm going to take 85, it's my first mass number, then I'm going to multiply it by my percentage, but I'm going to want to make sure that I'm using my percentage in decimal form. So I'm going to write it as 0.722 instead of 72%, okay? So I'm going to write it in decimal form. And this way, it makes our math at the end a little bit easier, okay? And I'm going to multiply those together, and I get 61.37. And then I'm going to do the same thing with my next isotope. So the next isotope, sorry, that's supposed to be a 5. My apologies, is 87 times 0.278. And that's going to be 24.186, all right? So I've taken each of my mass numbers, okay? There's 72% of this, and there's 27% of rubidium-87, and then I just add them up. So I take these two, and then I add them, okay? And that ends up with 85.556, which we can round to 85.56, all right? And that is going to be my average atomic mass. And we're going to use a unit of AMU. That stands for atomic mass unit. So make sure you write that down. AMU means atomic mass unit. All right, for our second example, we actually have 3 isotopes here. We've got 3 isotopes. We're going to use uranium. So remember, we're going to use our mass number multiplied by our percent abundance. This problem is a little tricky, not just because there's 3, but because these percentages are so small. So you want to do 0.0001. It's going to be in decimal form. So I'm just going to convert these all first so that they're a little bit easier to read. 0.0071. And then this one will be 0.9928. Okay, so let's start these out. I like to start with my smallest isotope going to my biggest isotope. So I'm going to have U-234 times 0.0001 equals. Sometimes I set it all up first and then I do my math, get the calculator out all at one time. So 235 times 0.0071, and this is easier for me because I've already, moved my decimals over a little bit. 238. You'll notice the isotopes aren't all one away from each other. Okay, sometimes they're a little bit farther away from each other. And the reason that is that some parts of the atom, some combinations of protons and neutrons are just more stable. Okay, they're just more stable. 9928 equals. All right, and we're going to get ready to add them. Okay, so let's do our multiplication first. I've got 0.0234 up here. I've got 1.6685 here, and I've got 236.264 down here. And you can leave the decimals large at this point, especially because we're working such small numbers. And then at the very end is when I want you to cut it off to 2 decimals, all right? So this will be 237.9783, and we're going to round that off to 237.98, and my unit is going to be AMUs. That's an 8 here. All right? So that is our average atomic mass. Again, our mass number times our percent abundance.